So section 3.2 is going to go over two theorems. We're going to split it up. One part's going to go over Rolls Theorem. The other part's going to go over something called mean value theorem. So when we do a quick recall, so it says a function is differentiable, meaning you can get the derivative, at x if its derivative exists at x, and differentiable on an open interval, a, b, if it's differentiable at any point in the interval. Okay, that's a little confusing to understand, so let's go over the specifics of how Rolls Theorem works. So number one, identify if f of x is continuous everywhere on the closed interval. So that's the same thing we did for extreme value theorem. So find out if the original function is continuous everywhere on the specific interval that's given, and it has to be closed. Step two, we're going to find the derivative, and we're going to find the critical numbers. So that's where the derivative is 0 or undefined. Still hasn't changed yet. Same what we did last time. We're going to identify all the critical numbers. Now here's the change, that fall in the open interval, AB. So I'm taking the closed interval and I'm just now making it an open interval. And then those are the values that would satisfy Rolls Theorem. So example 1 says, determine whether or not Rolls Theorem applies, explain why or why not. So all we're doing is saying yes or no with something to back it up. So if I were to sketch this first one, I'm going to sub my points in. So if I sub 0 in, 0, if I make myself a little chart here, I'm going to just do 3 points, 0, 1, and 2. So if I sub 0 in, I've got 1 minus the absolute value of 0 minus 1. This is negative 1, which is positive 1, so this gets me 0. 1, when I sub 1 in, that's going to get me 1 because that's 0. So 1 gets me 1. When I sub 2 in, 2 minus 1, that's also going to get me 0. And all we have there is this little guy right here, because it's just that little piece. So it says, determine whether Rolls Theorem applies. So identify if the function is continuous on the closed interval. So yes, it's continuous. So yes, continuous on the closed interval from 0 to 2. Okay, so since it's continuous, we can then say that Rolls Theorem applies. Okay, and that's all you're doing for this part. We're not focusing on actually figuring out the values. That'll be later on. The directions will also change. All right, for the second one here, if we sketch this, so if I sub in the values that I have, negative 5, negative 4, negative 3, negative 2, negative 1, and 0. If I plug in negative 5, I get 3 over negative 1, which is negative 3. If I plug in negative 4, that's undefined because there's actually a vertical asymptote there. If I plug in negative 3, I get a positive 3. If I plug in negative 2, I get a 3 halves. If I plug a negative 1, that's going to get me 1. And if I plug 0, I get 3/4. So 1, 2, 3, 4, I have a vertical asymptote there, so it can't equal that value. I've got the point negative 5, negative 3. Negative 3, 1, 2, 3. Negative 2, 3 halves. Negative 1, 1. 0, 3/4. And you're going to see this little arch going here. The only thing is I have to make sure. Let me go back and fix this. I can't go beyond the 0 because that's where this stops. Okay, so it stops there. And on the other side, if I'm only going from negative 5 to 0, I can include this little piece right here. So when you look at this, you say, okay, well, if I put my pencil down and I follow this function from left to right, it's not continuous. So this is not continuous since there is a vertical asymptote at x equals negative 4. So that means Rolls Theorem does not apply. So always be able to back it up with y. All right, so now let's get to the actual algebraic part about it. So it says use Rolls Theorem to find all values of c. So first thing you do is you look at this function, you say it's a polynomial, so yes, it's continuous. So we're good to go. So I'm going to keep going. All right, so it says I'm going to take the original function and I'm actually going to distribute the x squared. So x to the 4th minus 2x squared. And I'm going to get the derivative. So I get 4x to the third minus 4x. I'm going for critical numbers, so I have to set that equal to 0. I'm going to factor out a 4x, keep factoring, and I get 3 critical numbers, 0, -1, and +1. Okay? Then, according to Rolls Theorem, step 3 is I'm going to check my critical numbers on now an open interval from -2 to +2. So the question is, does 0, -1, and 1 all fall within that interval, which they do, which means my C values or my critical numbers are 0, -1, and 1. If 1 did not, you just don't include that value. All right, sine function here. So yes, it's continuous, which means we can keep going. Again, if it's not, you stop. My function is the sine of 2x. The derivative of that would be cosine 2x times 2, which is 2 cosine 2x, which I'm going to set equal to 0. I'm going to divide the 2 over, and I'm looking for values where the cosine of 2x is 0. So what you want to think is you want to think cosine equals 0. So where does the cosine equal 0? Well, that's at pi over 2 and 3 pi over 2. So this is where the extra piece comes in because you have this 2x going on here. So what you're going to do is instead of pi over 2 and 3 pi over 2 working, because if you sub them back in, they don't work, you have to then take that value in the cosine function, the 2x, and set it equal to each one of the values you just came up with. So instead of pi over 2, you're actually getting pi over 4. And instead of 3 pi over 2, you're actually getting 3 pi over 4. And those are your critical numbers. So now what you're going to do is you're going to check on the open interval, pi over 6 to pi over 3. Okay, pi over 4 works, but 3 pi over 4 is outside of the interval, so that one doesn't count. So your C value is only going to be pi over 4. And you can just say outside interval. So again, 3 pi over 4 doesn't work out. All right, let's keep going. So it says use Rolls Theorem. We've got this function right here. It's a polynomial, so no matter what, yes, it's continuous, which means I can keep going. So in order to get the derivative, you have the option. You could do product rule, but you see you have power rule and chain rule incorporated. Or what you can actually do is just FOIL the whole thing out. It does make it easier. So x squared 2x1, FOIL it one more time. You get x to the third minus x squared minus 5x minus 3 when you combine like terms. The derivative is then 3x squared minus 2x minus 5, which you can factor into these two polynomials. Set it equal to 0, and you get 2 critical numbers, 5/3 and -1. Keep in mind, though, you have to check on the open interval from -1 to 3. 5/3 is okay, but -1 is not part of that, okay? So let's make a little note. So it is not in the interval -1 to 3 because it has a parentheses here, which means your only C value is going to be 5/3 for this one. So don't forget to check it on the open interval. All right, for this one, we've got f of x equals the tan function. If you remember, if you sketch the tangent function, also remember tangent is sine over cosine. So you can't have a denominator equal to 0. So this can't equal to 0. And you know that it already equals 0 at the denominator equals 0 at pi over 2, which means negative pi over 2 would apply. And then you can say 3 pi over 2. So if you sketch this, because pi is about here, you basically have half of your curve going on here. Okay, now, these are asymptotes. Okay, so the first thing you say is you look at this and you say, okay, well, given that interval, you can say the tangent of x is undefined at x equals pi over 2. So tan x is not continuous. Therefore, Rolls Theorem does not apply. Okay, and if it doesn't apply, you can't move any further. Now keep in mind, the interval, it's not always going to be this for tangent. If it had been pi over 2 and negative pi over 2, you could have kept going. But you always got to focus on what that interval is first. All right, last one here. It says find two intercepts, or find the two intercepts of f of x squared minus 3x plus 2. So let's do that first. So for the intercepts, we're taking our function and we're setting it equal to 0. So I'm going to factor, and I get two intercepts, x equals 2 and x equals 1. There's my intercepts. Part 2 says that show that the derivative equals 0 at some point between those two intercepts. All right, well, my derivative would be 2x minus 3. Set it equal to 0, and I get x equals 3 halves. So x equals 3 halves falls between x equals 1 and x equals 2. Okay, so you're just justifying the fact that the intercept, or the